Um, Hello, everybody. Welcome to the lecture 5 of Introduction to Differential Privacy. We're gonna continue to talk about the differential privacy basics and cover a few more building blocks of understanding differential privacy and learning the analytical techniques to analyze and study these methods. So before we get to the actual course material today, I have a few logistic notes that I wanted to tell you guys in person. So if you haven't started to think about your course project, I think now is a good time to start thinking about it. So I've shared a list of ideas on Piazza. So you can click in that link and go to a Google Doc, and there will be papers for each individual ideas. Yeah, you don't have to pick any of them, but if you do, or if you want to do something else, then it's like you should start forming your own team, or just doing your independent project. Decide on doing your independent project. And if you have anything that you want to discuss with me, like feel free to send me emails or notes on Piazza, or come to my office in person. Just make an appointment by email, and I'm happy to talk to you. And some of those ideas may lead to publishable research projects, and others are more for the educational purposes. So you can, they have a different level of requirement. The most basic type of projects more or less just involve reading, like reading 1 or 2 papers and implementing what they are doing, and sometimes understanding their proofs. Yeah, so the projects are quite flexible, and if your own research has something to do with differential privacy, or you want to develop a differentially private algorithm for the type of method that you're working with in your own research, so that would be a highly appropriate project for this course. Alternatively, you can just pick one of the things that I've put in there, and many of them will like doing any one of those that I listed will ensure that you learn something from the project. Yeah, another thing is about scribing. So thanks to those of you who have already scribed the lecture 1 and 2, they are now available on the website. So they are the same material as the lecture, but the student sometimes could take the liberty of enriching the materials a little bit by providing more background knowledge if you look into the related references and so on. Yeah, so when if you haven't signed up for scribing, there is a spreadsheet that you can find on the course website to sign it up, and each lecture, it's just this much of material. So typesetting what I talked about in the class into a shared scribe will help us to keep track of where the course is going, and at the end of the day, we'll also have something in written that we all could collectively keep as a record. Okay, so once you are done, just send me the LaTeX file. I may get back to you with some comments and suggestions, and once you fix them, so I'll just put it on the website to make it available to everybody. All right, so let's start our recap of the last lecture. So last time we finished talking about the so-called sparse vector technique, which is one way to answer a possibly exponentially many queries by selecting those that are interesting. And at the end of the day, you effectively pay only for those that your algorithm find interesting, which could be just a constant number when the total pool of those queries can be exponentially large. And then we talked about the problem of linear query release and applied various techniques to this problem, including just using the Laplace mechanism to answer every query and compose over the multiple access to the data, publishing the contingency table or the histogram representation of the data directly, and then try to come up with estimators to use it to answer linear queries. And the most interesting part of the last lecture is this private multiplicative weight algorithm that combines the idea of this sparse vector technique, which does selection, and then combine that with a particular no regret online learning method called the hedge, or the randomized multiplicative weight algorithm, and that ended up giving us an error, like a epsilon differentially private algorithm that depends only logarithmically in the size of the data space and the size of the query space and the number of online sequence of query. Let's take a closer look at this private multiplicative weight. So the key idea of this algorithm is to learn a synthetic data set while answering queries. And this synthetic data set, you can think about it as some hypothesis that your like machine learning algorithm is keeping track of. And it learns online, and from the guarantees of this online learning algorithm, you will know that it has no regret. And then like we use the sparse vector technique to check if the error of the synthetic data on every new query is large or small. If it is small, then we just use the synthetic data to answer the query without incurring any additional privacy loss. On the other hand, like if the synthetic data is doing very poorly on this example, then we're gonna ask the data to give me the true answer. So you can think about this as some kind of active learning where you are only asking for those labels to those examples that will somehow improve your current belief of what the right model is. Okay, so you're only spending privacy budget for those queries that are worthwhile for improving your accuracy of the synthetic data. So what we can show from the regret analysis is that the number of runs that this online learning algorithm executes is bounded from above by some like O tilde 1 over 1 over alpha square, where alpha is a desired error that we want for the for answering the sequence of query in max norm. And this O tilde hides a logarithmic dependence on just the sequence of queries that we are answering. Okay, so what the regret bound of the multiplicative weight algorithm says that after this many rounds of queries that actually cost privacy budget, the synthetic data set will take over and will no longer be asking for like any more actual like actual answers from the actual data. Everything will be handled by the synthetic data set from this point onwards. Right, so it's an algorithm that makes perfect sense, and it is a combination of interesting ideas from two different communities. Yeah, so it's kind of a nice algorithm. Okay, and if we summarize this problem of private query release, answering a sequence of k normalized linear queries, then if we just put all the errors together, we can see that if we use a Laplace mechanism to release queries and compose on the fly, and then we get this k over n epsilon, right? So this is as if we are just answering a small number of queries, and this is doing like very well, and in fact it is doing better than the statistical error, which is 1 over square root of n. And if we want to answer a huge number of queries, then and say an unbounded, almost unbounded number of queries, then we can just directly and especially when the data space is discrete and small, then we can directly try using Laplace mechanism to publish the histogram of the data set itself, and that also gives us that also gives us the 1 over n epsilon rate, but there's a polynomial dependence on the size of the data space. And notice that for d Boolean features, the cardinality of the data space is 2 to the power of d. right? If you have continuous features in some coordinates, then this number will get even larger. But the exponential dependence on D is not really avoidable here, like using the second approach. Lastly, if we use a private multiplicative weight, then we get the best of both worlds. We get a log K and also log we get log K and also log cardinality. So this will be something like a dimension, or more generally, like if you're familiar with machine learning, you can use some other uniform convergence trick to get this D to be the VC dimension or other complexity measure. And the log K is a total number of adaptively chosen linear queries that you select. Right. The cost of doing this is that now it goes to 0 at a slower rate rather than 1 over n epsilon. Now it goes to 0 at a rate of 1 over n to the 1/3. And like computational complexity is a dimension that we didn't talk about in the last lecture, but as we can see, among the three algorithms, the only algorithm that's computationally efficient in the sense that it is a polynomial in everything, in all the parameters, is a Laplace mechanism just to directly release a query. So all the other two methods actually depends exponentially on the dimensionality, which sometimes makes these algorithms infeasible to run in practice for very high dimensional data sets. Okay, but yeah, computation is not the main focus of this course, but we wanted to keep these considerations in mind, because sometimes there are also efficient algorithms, maybe not efficient in the worst case, but in some sense oracle efficient algorithms that can be used to implement these methods in ways that are computationally more efficient in practice. Okay, and we also talked about the problem of private selection in the last lecture. So private selection is a problem of finding the most appropriate item from a set of items where each item is evaluated by something called a utility function. This utility function takes a private data set X and a particular item R, and it outputs how good this item is, how much utility is going to give us. And the problem of private selection wants to do the maximization of the utility function over the space of items while satisfying differential privacy for this other input of this utility function X. Okay, so we learned like one mechanism to do this called the exponential mechanism, which the idea is to just exponentiate this utility function and then sample with probability proportional to this exponentiated utility function here, exponentiated. So the idea behind the exponential mechanism is that we want to make those high utility items exponentially more likely, while making those low utility items exponentially less likely. On the other hand, like since this is exponentiated and also since this utility function itself, as we change X to a neighboring data set X prime, then the total amount of changes of this U, the max amount of changes to this U is bounded by the global sensitivity of this utility function. So notice that this needs to apply for every R. Then this exponentiated sampling also serves some kind of a smoothing, which smooths out the maximization and replace that with sampling from a distribution that best approximates the argmax. Yeah, this is closely related to the smoothing tricks that's commonly used in machine learning, called the softmax trick, that replaces the maximum with a softmax, replaces the argmax with log sum exponential, and so on. And the privacy analysis for the exponential mechanism, which is the last thing that we covered in the last lecture, is quite straightforward. So notice that this distribution is defined up to a normalization constant, right? So depending on what U is, this doesn't necessarily add to 1. right? When you sum over all the possible random variable R, all the possible values of R. So the actual distribution is e to the power of u x comma r over 2 delta u divided by the sum or the integral over all possible R, u of x r. Yeah, let's call this r tilde, 2 delta. Yeah. So when we prove the privacy property of exponential mechanism, it suffices to bound the ratio of the numerator and then also bound the ratio of the denominator. And each one of them contribute e to the power of epsilon over 2 factor. So in total, it gives us e to the power of epsilon blow up multiplicatively to the density. Suppose you change this input data set from x to x prime. Okay. So yeah, in this lecture, we're gonna finish the topic on private selection by first analyzing the utility of exponential mechanism, also give a few examples of exponential mechanisms to connect it to what we've learned before. And we're gonna apply exponential mechanism to the same familiar problem of releasing many linear queries and using an algorithm called small database or small DB. And then we're gonna talk about an alternative approach for private selection called report noisy max. And after that, we're gonna start to talk about approximate differential privacy or epsilon delta differential privacy, and introduce this concept of advanced composition so that we can get a little bit more mileage of some of those things that we've learned so far. Okay, so that's the game plan for today, and the reading materials as is listed on the course website are just our textbook on algorithmic foundation on differential privacy with chapter section numbers given here, and for the advanced composition, I'm gonna cover something that's slightly different from what Dworkin and Rose did in a book, which is slightly more general, and the Vathan's tutorial is a good reference for it. But what I'm going to be covering is also like slightly different from Vathan. Yeah, we will see what are the pros and cons of doing that. But at least the analysis for the advanced composition that I will be covering is going to be slightly simpler. All right. So yeah, the first thing that we're going to be doing is to like give a few examples of exponential mechanism. So I argue that the two mechanisms that we learned, the randomized response and the Laplace mechanism, they're both instances of exponential mechanisms. Especially when we just consider like the distribution that they're sampling their outcomes from. So what does randomized response look like? So the input is just a bit, 0 or 1. And the randomized response outputs the just x with probability e to the power of epsilon 1 plus e to the power of epsilon, and it outputs 1 minus x with probability 1 over 1 plus e to the power of epsilon. Okay, so this is a I guess an exponential mechanism because the distribution is defined as following. So let's say that the output is y. The probability distribution is exactly written down here, and it is I guess obviously proportional to e to the power of epsilon indicator of whether y is equal to x. If y is equal to x, then you get this numerator e to the power epsilon. If this indicator is not true, then you output is 0, then you get this 1. Okay, so it is clear that this utility function by taking u of data set and output is equal to indicator y given y is equal to x is one valid like utility function used to define the exponential mechanism, and it gives the same mechanism over here. Okay, so what is the sensitivity of this u, x, comma, y? So as you change x from 1 to 0 or 0 to 1, this changes at most 1, right? So the sensitivity of this u is 1. Okay, so now let's think about Laplace mechanism. So Laplace mechanism takes a query f of x that is known to have f delta f to be its sensitivity, and Laplace mechanism outputs fx plus Laplace noise with the noise proportional to delta f over epsilon. Okay, if we write down the let's say that this is output that's defined as y. So the probability distribution of this y is equal to 1 over I guess epsilon delta of f and e to the power of minus fx minus y absolute value over, I'm just writing down the probability density of the Laplace distribution, and this is epsilon over delta of f. Yeah, I think I'm missing a factor of 2 here. Yeah, this is the probability density of Laplace distribution. We can see that this distribution is also just proportional to this quantity, right? Then we can say that the utility function for the Laplace mechanism is just minus f of x minus y. So that would be the utility function. So again, like we can try working out the utility function of ux comma y using the utility working out the sensitivity of this utility function using the sensitivity of the query f itself. Since this is just absolute value and y is y is fixed, then delta of u, I argue that this is smaller than delta of f. Right. So in case of counting queries or other linear queries, this delta f is 1 for unnormalized linear query and 1 over n for normalized linear queries under the add or remove under the replace one neighbor relationships. Okay, so we can see that both these two mechanisms can be defined as an exponential mechanism, but there's one small issue. So if we remember the exponential mechanism, there is actually a factor of 2 multiplied to this delta of u. So if we want to, I guess if we want to just directly use these utility functions to derive the exponential mechanism, the exponential mechanism version of the randomized response when u xy is equal to indicator whether x is equal to y is gonna sample from a probability distribution where this is defined up to scale to indicator epsilon indicator x equal to y over 2. Similarly, the Laplace mechanism, exponential mechanism version of the Laplace mechanism will have something like this: 2 delta of f, and the same as delta of u, and minus epsilon y minus f of x. Right. So this factor of 2 here, yeah, and from the generic theorem for exponential mechanism, it says that these mechanisms are epsilon dp. On the other hand, due to this additional factor of 2, we know that if we just use the direct analysis of these two mechanisms, we can show that they both satisfy they both satisfy half epsilon dp. Right. So there's sometimes like a factor of 2 difference in using the heavier weight machinery to analyze the same mechanism comparing to just doing a more straightforward direct analysis of these individual mechanisms. And what's really going on here? So recall that in the exponential mechanism, we are bounding the multiplicative, we're bounding the densities by bounding the numerator and bounding the denominator separately. And it turns out that for both these two mechanisms, the normalization constant, they're constant. They're completely independent to whether the input is x or x tilde or the neighboring x prime. So that saves us a factor of e to the power of half epsilon. Yeah, if you look at the proof. Okay, so what's really happening is the following. So there are like two different types of exponential mechanisms that's often confused, that people often confused with each other, because to define the same distribution, there are multiple different ways of choosing this utility function. It is entirely possible that you choose this u to be one thing, and you choose this u to be something that's completely different. And at the end of the day, you are getting the same output distribution. So apparently, this output distribution will satisfy the same privacy guarantee, but then the sensitivity of this u might be hugely different. The first type of exponential mechanism is a standard exponential mechanism that we've learned with an insensitive utility function. For every utility function, we can ignore the normalization constant and specify the algorithm as this. And both the randomized response and the Laplace mechanism actually qualifies to be a second type of exponential mechanism with insensitive log probabilities directly. So the key difference is whether this is defined proportional to or whether this is equal. When you factor in the normalization constant, then you can rewrite these two special cases to be the type 2 exponential mechanism, which gives you a factor of 2 improvement. So for any u, they're always so for any such u satisfy that the sensitivity the sensitivity is delta u. There always exists u tilde in the type 2 such that the delta of u tilde is smaller than 2 times delta u. Yeah, the converse is just like a factor of 1, right? So these really have motivated some recent research work by Durfee and Rogers in improving exponential mechanism and analyze it more carefully, so that at the end of the day, for the type 1 kind of exponential mechanism, you can more or less get away with the same kind of privacy analysis if at the end of the day you're hoping to you're hoping to compose many rounds of these mechanisms for many rounds. So I won't be able to cover that, but for those who are interested in this discussion on how to improve this constant factor, which actually matters a lot in practice, you can check out Jin Shuodong's blog and also this paper. Yeah, yeah, that's a detour for us to understand the exponential mechanism a little bit more deeply. So now let's get back on track and analyze the utility of exponential mechanism. How should we think about this? So exponential mechanism tries to sample an item with high utility, right? So the right way to say that my output is good is that I'm getting an output that is close to being optimal, right? Let's say that my output of the exponential mechanism is alpha optimal. It says that comparing to the best possible item in the set, mine, the one that I output with high probability is at most at most alpha away from being optimal. Okay, so this theorem says that the utility of what the exponential mechanism, okay, of the what the exponential mechanism output is smaller than this actual optimal solution minus some numbers which we'll call alpha. Okay, and the theorem is about the relationship between this alpha and this failure probability delta. So with high probability 1 minus delta, then this this utility is alpha suboptimal when alpha depends on the choice of delta and other system parameters. Okay, so that's what should we analyze it. So let's move ahead and try. So first of all, I argue that it suffices to bound the probability that this mechanism outputs something that is not alpha optimal. Okay, so we'll first define like this so-called super level set. Let's say that the horizontal axis is a space of all possible items, and the vertical axis is a utility of each individual item on this particular data set. So let's say that this is a complex looking function like that. Okay, with this different alpha, and we define this is its optimal solution. The optimal solution appears at this R star, and this is what we call OPT. And to say that this is alpha suboptimal, we get this is alpha. And if we draw a horizontal line here to cut through this figure, then and these regions that are highlighted, they are the so-called super level set, which we call R alpha. So this is defined to be the set of all R such that the UX of R is larger than OPT minus alpha. Yeah, this is called the super level set. Okay, so I argue that it suffices to bound the probability that the exponential mechanism outputs something that's outside this set. So probability of M of X is not in R of alpha. And this is by definition is equal to just sum over all. Let's enumerate, or you can do this as an integral if this is really continuous of R of alpha. Then the probability of output. Okay, and now by the definition of exponential mechanism, we know that this is exponentiated e to the power of epsilon u x r over 2 delta u. And then there's also this normalization constant. And for each one of these R, this normalization constant is the same. So I'm dividing R tilde in all of these R and e to the power of epsilon u x r over 2 delta of u. Okay, so far this is clear, right? I'm just applying the definition. And now let's try to upper bound this probability by providing an upper bound of the numerator and providing a lower bound of the denominator. So since they're both non-negative, so we can get away with writing this inequality. So what we know about the numerator is for any of these R, so this is R complement, right? So this is not in rather not in R of alpha. So what we know is that these are at least alpha away from being optimal. Therefore, we can upper bound this by exp epsilon OPT minus alpha. Yeah, because this is the largest possible value that any of these R could possibly attain. So these are sets over here, and over here. For all these R's, so we know that their values is always smaller than OPT minus alpha. Therefore, we can take this as upper bound. How about the denominator? So the denominator is the sum over everything, and what we know is that this everything actually contains the optimal solution. right? So the optimal solution is being added, and everything is non-negative. So we can just drop everything else and just keep the keep the optimal R star. And then suppose there are multiple R stars. So let's say that this optimal parts can be flat. Then there are multiple items that are within that set. Then let's keep all of them, right? So we can lower bound the numerator by just sum of R in R0, and R0 is the set of all optimal solutions that actually attends OPT alpha. Okay, then this will be exp and epsilon OPT over 2 delta of U. Okay, now the numerator and denominator, they are constant, so it becomes just a simple counting argument, and this becomes that we can further upper bound the number of items that we sum up in the numerator by the space of all R. So this is smaller than R cardinality and divide by R0 cardinality. Yeah, I guess this R0 is just R OPT in the theorem statement. And then what remains is that we can just merge things on the exponent. We're left with epsilon minus alpha. Oops. Just one moment. Sorry about it. Okay. Okay, so this is what we got, and then it goes to 0 exponentially as alpha gets larger, and with some polynomial number multiplied in front of the exponential factor. So we know that at the end of the day, when we set this to be delta, we can get alpha to be 2 delta U over epsilon log of R over R OPT cardinality over delta, right? So that's what we got from the theorem as well. Okay, so that's the idea of how this is worked out. It basically just comes from the definition of exponential mechanism and the fact that there exists one optimal solution, and everything else that are not alpha optimal has exponentially smaller probability of being selected, right? And this argument is not very tight, and you can obviously come up with all sort of additional conditions to analyze the exponential mechanism more carefully. For instance, some type of growth condition and decay condition will make the bond substantially better. But this is just the most general and assumption-free analysis of exponential mechanism. All right, so one of the things that we can do with exponential mechanism is to actually apply it with a very simple algorithm to the problem of linear query release. So let's say that we are giving a fixed set of query of a size k. In other words, where the cardinality of this query space Q is equal to k. And now instead of doing randomized multiplicative weights to try coming up with the synthetic data, so let's just run exponential mechanism to select among the space of all possible data set to find one synthetic data that's most consistent with all these queries. So in this case, now that this is a fixed set, an offline set of queries, then we can, in principle, just evaluate all of them, get the true answer from the data, and then try to find differentially privately output a database that matches with those answers most accurately, right? And in addition, since the previous utility analysis of exponential mechanism depends on the cardinality of this space that we sample from, let's consider databases that are small, right? So let's consider the space R to be the set of all data set where the data set contains at most this many elements in it. so that's the idea. And the hope is that within this set of R, there exists one data set that can be used to answer all these queries sufficiently accurately. And also, like if we use exponential mechanism from the utility guarantee of exponential mechanism, we will be able to find output a solution with high probabilities that are not too far apart comparing to that optimal solution within this R. Yeah, there are two issues here. So the optimal solution is not really the actual data set, because the actual data set might have the number of data points that's much larger than this log Q cardinality over alpha square, right? So it's not really realizable. And the second thing is that the suboptimalities that are required by the exponential mechanism might be hurting us, right? So by combining all these two factors, it forms the right utility analysis of this algorithm, small dB. Then it's small dB because we are artificially making the space of the data set that we're sampled from small. So is the algorithm clear? Yes. Okay, yeah, I didn't explain that. Yeah, the utility is defined to be, so this X is the actual data set, and this Y is some data set from this R, right? It is somehow a small data set. And the utility function is defined to be the largest error on all of possible queries, like the largest absolute value of error difference between what this synthetic data set Y would have given comparing to the ground truth, right? And max over the set of all queries, right? So it's in some sense an L infinity norm distance between fx and fy. Okay. And then we basically use this to run exponential mechanism. Okay, so the privacy analysis of the small dB algorithm is straightforward because it follows from that of the exponential mechanism, and all we have to do is to show that this utility function is actually low sensitivity. So for the for this part of the yeah, to be consistent with what we did in the SVT, let's consider this F to be normalized linear query. Yeah, normalized, it means that this F of X is equal to some kind of a Q transpose X over 1 over N, and this N is a size of the data set. Okay, and yeah, let's also consider the neighboring the replace one neighboring relationship so that this N is public information and we don't need to worry about it. Okay, so the utility function looks like this, and it is clear that this utility function also satisfy like bounded sensitivity. So for any two neighboring data set, X and X prime, that are neighbors, this is defined to be, yeah, there's also max over Y here. This is defined to be xy minus U of X prime Y. And by substituting this definition inside here, you just have a bunch of max that's outside, and inside you get max of F in all of the Q, F of X minus F of Y plus max of F in all of the Q, F of X tilde minus F of Y. Right? And this is, yeah, notice that these are distance functions, and these are the differences of two distance functions with the input being the difference of f of x and fy, and we can apply triangular inequality. Right, so think about this max as L infinity norm, and with this norm, then we can apply triangular inequality, and this is smaller than max of y, max of x prime, and max of f inside the Q and f of x minus f of x prime. And then we can just swap the order of these two, right? So they are all maximization over the different parts of the argument. We can just swap the order of these two, and what we get is max of over y is independent to y already, so we can just drop that, and max over f in all the query space, and max over x prime that are neighbors, fx minus fx prime, and this is smaller than just global sensitivity of f. Actually, the max global sensitivity of this query class. Okay, so we've already seen that since f has this form and q is in 0, 1 to the size of the data set, then we know that this is on the order of 1 over n. Okay. So with that in mind, we can so with that, so basically we can apply exponential mechanism and using this utility function, and the form of this exponential mechanism will be to output y with probability proportional to e to the power of I guess e to the power of minus max f in q, f of x minus f of y, multiply by epsilon, divide by the sensitivity, 2 times the sensitivity, 1 over n, right? So this n gets up to the minus n epsilon and this max utility function. Yeah, so that I don't feel like writing it down, but you can see that this n gets up to the numerator, and this is a very concentrated probability distribution, like around its optimal solution. Okay. So how do we analyze the small dB algorithm for the sequence of linear queries? So like I explained earlier, so this algorithm works because of 2 things. So first of all, if we need to be able to find that there exists a small data set, that like approximate the big data set on all queries within this query class, right? It needs to approximate really well. So because otherwise, even if we are able to just directly output the argmax of the utility function or argmin of the max error, then the result won't be good. And secondly, it is the approximation that's coming from exponential mechanism, and we need that approximation ratio. Like we need that distance from the optimal solution to be also small. So by balancing these two, we end up getting like some interesting rate. So I also argue that these are actually contradictory with each other. The more we enlarge the size of the data space that we sample from in the exponential mechanism, the first approximation error gets smaller, but it makes the exponential mechanism a little bit harder to get to the optimal solution. On the other hand, if we make this R like very, very small, if we consider a data set that are like very small, then exponential mechanism will be very easy because it always gives me something that's very close to the optimal solution within the class, but the class itself like might not approximate the original data set that well, right? So it's a matter of balancing these two. So let's say that we are according to the algorithm, we're choosing this size of the data set to be on the order of log Q cardinality over alpha square, right? So without loss of generality, let's consider the case when this is smaller than n. I'll leave it as an exercise. What happens when this is equal to n or larger than n, because that really trivializes things. Now, so I'll leave that an exercise. And for now, let's consider those situations where our choice of the small data set is actually smaller than the given data set itself. Now, like the claim is that there always exists a small data set that is alpha accurate when we choose the size of this small database to be on this order. And the idea is nothing but just doing random sample. So in fact, let's do IID sample with replacement from the discrete distribution that's given by the data set. So this is assigning a probability of 1/n for every element of this data set, of this input data set X. Probability Xi is included. Yeah, so basically IID sample from yeah. So I don't know what is the right notation for this. Maybe the probability simplex of X. Right, so this is a familiar notation that we use. IID sample for let's say M is equal to log Q over alpha squared. So we'll show that this works. Since this is IID sample, and also we know that from the IID sample by Hopkins inequality, and also like individual samples of this actually satisfy boundedness, because this Q of, yeah, recall that this linear query has a statistical query interpretation. This can be written as 1/n sum over I from 1 to n, and this individual phi of I, and some f of Q, right? And we know that f of Q of phi of I for any phi of I is larger than 0 and smaller than 1. Okay, so because of this, we can apply Hopkins inequality to bound the mean of the small data set compared to the actual data set. So what we can do is to say that for a fixed f in the query space with probability 1 minus delta 1/n, this is a ground truth, and minus the 1/m, where m is this number. This is your sample. Q transpose. Let's say that the random sampled database is X tilde. This is smaller than. This is smaller than, I guess, by Hopkins inequality and the fact that these are bounded, log 1/delta. Okay, so this is by with probability 1 minus delta. Now we can take union bound, union over all f in. Then we can get with probability by simply choosing this delta to be Q, like delta tilde over Q with probability 1 minus delta tilde. Then we can get that the max over all Q in this query space. Okay, so this looks like an error bound, and the reason why it works is this Q transpose X when X is an actual data set in the like standard data table representation, and there is this statistical query interpretation of every linear query, and then you can rewrite this as a summation, as an average. So what this basically says is that the empirical mean with M samples converges to the population mean. Empirical mean converges to the actual mean. Okay, so why does it help us? So notice that we wanted to show the existence. So as long as there is a probability that is smaller than 1, as long as there's a non-zero probability that our sample will return something that is our sample will return a database X2 that is close to that is close to this X in alpha, then we know that there exists, because the probability of seeing it is non-zero, right? So all we have to do is to simply choose this delta to be, say, anything that's smaller than 1. So we can choose it to be, say, 0.0.99, or we can choose it arbitrarily close to 1, right? By choosing this delta to be arbitrarily close to 1, and then we can work out the relationship between the required m and this size of alpha. So let's square both sides. So we get log of q over 2m is equal to alpha, and this requires this alpha to be this requires this alpha to like m to be log of q over 2 alpha. Yeah, but which says that if we choose this m to be this quantity, then it is sufficient to alpha r squared, to alpha squared. So this implies the existence of a small database that is alpha accurate. Okay, so is that argument clear? So provided that if you sample, provided that there is a probability that's strictly smaller than 1, then that implies that there actually exists such a database. Okay, so this shows that if we sample this many, then the OPT is larger than like n times alpha. Yeah, so notice that this is normalized, right? So this alpha is normalized, therefore we're multiply this by n. Okay, let's keep that in mind and move to an application of the utility theorem of the exponential mechanism. So do we still remember that? So so this basically the utility of the exponential mechanism basically says that what the with probability 1 minus delta, the output of the exponential mechanism, yeah, so U of data set and the output, and U of X of R star minus that is smaller than some alpha parameter, and that alpha parameter is let's maybe go back and check it. Yeah, this is utility, and we've worked out that this alpha is 2 times the sensitivity over epsilon multiplied with the log of the cardinality of this R, right? And this cardinality of R OPT is always larger than 1, right? So we can just set it to be 1. So what we get is 2 times the delta of U over epsilon log of R cardinality over OPT, and we are just replacing this by 1 and then divided by delta. Okay, so that's the utility for the exponential mechanism. So in this case, we just worked out that the delta of U is 1 over n. So this is 2 times n epsilon log of R over delta. And what this further says is that this U of X, M of X, is larger than, if we just move this to the right hand side, and then if we move this to the right hand side and then consider this one, like just now in the previous slide, we've shown that this one is close to being like yeah, so let's maybe try yeah, this is not actually the R star. This is R star within this is R star within the small database, right? We know that this R star within the small database it is close to, it is also close to being optimal by n times this, by n times this alpha parameter. Okay, so what we can so ultimately what we want is this one is larger than u of x yeah, OPT my plus OPT minus OPT, and then plus u of x of this R star. So this is coming from the best within the small database. I'm just adding or removing this global optimal solution, and minus 2n epsilon log of R over delta. Okay, so what we've shown in the previous slide is that this is proportional to n times alpha, and now it remains to substitute what is cardinality of R is, right? So the cardinality of R, like as we've worked out, is alpha square. I guess yeah, the cardinality alpha square is a cardinality of x to the power of m, and we know that m is alpha square log q, right? So the log of R is what? So the log of R is, so this is n epsilon log of q over alpha square log of x, right? So what we got now is the, wait, yeah. Yes, so sorry about the confusion. Like I shouldn't I shouldn't add this n here. So this is unnormalized query. So this alpha is a right alpha to consider, right? So the alpha that we get from the difference between the average query is actually the right alpha to consider. So there's no multiplicative factor of n over here. So what we got is that this is alpha and this is this quantity, and minus alpha minus this quantity. So these two together is a total suboptimality that we want to consider, and it remains to choose alpha optimally to minimize error. So also if we substitute the difference between these two, we can get that we can get what the what this utility mean is the m of x if we substitute into this f minus f of the actual data. So this is ultimately what we want, and by triangular inequality you can bound this between by the difference of these two, and this is smaller than alpha plus 2n epsilon alpha square log of q log of x. So this should already be familiar with you, and it remains to minimize over alpha, and what we can do is to take the derivative and set the derivative to 0, since this is convex in alpha. So if we take the derivative, we get 1 plus 1 minus 4 over n epsilon alpha to the alpha cube log of q log of x cardinality, and by setting this derivative to 0, we can get alpha to be on the order of n epsilon log of q log of x, log of q log of x, and to the power of 1/3. Okay, so this is the same number that we get from the online method via the sparse vector technique and the random and the hedge algorithm from the last lecture. Okay, so as a checkpoint, so far we've applied the exponential mechanism to the small database algorithm by just doing exponential sampling over databases that are small, and both actually achieve the same asymptotic error of the form of n epsilon log of q log of x with some minor difference in the dependence on the failure probability delta, but both of them, if we choose delta to be a constant, they satisfy like this error bound. There is a small but important difference between these two algorithms though. So for the small DB algorithm to work, this set q needs to be fixed and available ahead of time. On the other hand, the multiplicative weight algorithm also works for the situations when this q cardinality is replaced by k, where k is a number of online queries that you answer, and adversary can choose this sequence of queries in ways that are adaptive. So multiplicative weight also allows adaptively chosen query as long as the length of the total sequence of query chosen is bounded by k, then you can get the same result by replacing its q's cardinality with its k parameter. Yes.
So for the small database, you don't need to replace. If you sample without replacement, then can you support online output? Like can you support like a string data set?
Yeah, the question is that in small database, like if you use sampling without replacement, rather sampling with replacement, can you allow answering a sequence of online queries? Yeah, the answer is no, because this is something that has nothing to do with how you create your small database, how you show that your small database exists. So notice that the sampling argument only appears hypothetically, right? So it is there for us to show that there exists a data set that is that has a small cardinality such that it approximates the original data set well. And in order to do that, in order to even run as the exponential mechanism, we need to be able to evaluate the utility function, right? And that utility function is defined to be the largest error for all possible queries in the predefined query space, right? So for that reason, small DB only works for the offline fixed set of queries. And sometimes you can come up with examples like this easily, that k can be exponentially larger than the cardinality. Yeah, sorry, it's the other way around. So the cardinality of q can be exponentially larger than k. Okay. Yeah, the catch is, however, neither of these two algorithms, they are computationally efficient, and that actually applies more general to exponential mechanism. So exponential mechanism is like almost never computationally efficient in practice when you are dealing with continuous space of these outcomes, and when you are dealing with a very large space of these outcomes, such as sampling like the synthetic data set. That like sometimes makes this algorithm like a theoretical object, and then people are still, it is still an active area of research to come up with practical and efficient implementation of these algorithms. Yeah, sometimes under additional conditions. All right, like it's 2:10. Let's take a 5 minutes break before we come back and talk about like a report noisy max. I do want to get to the second half of the lecture on advanced composition and approximate DP. So we'll do a quick coverage of report noisy max after the break. So I'll see you guys at 2:16. Hey, hey everybody, welcome back to the lecture. So let's continue to talk about private selection. So just now we talked about exponential mechanism and gave a few examples of it and applied that to the problem of linear query release. Exponential mechanism is one popular method, but it's not the only method for private selection. There are others. So one of them is called the report noisy max, or like more precisely, is the report noisy argmax. ARG, report noisy argmax. So here's the algorithm. Let's say that we are given a utility and which is low sensitive, which is insensitive, and effectively we can try adding noise to the utility function and create a randomized version of this utility function you have by just adding Laplace noise. Okay, so the amount of noise that we add is as if we are like trying to satisfy the epsilon dp with the Laplace mechanism, but with this additional factor of 2 that's in front. And then what we basically do is to output the argmax from the perturbed version of the objective function. Okay, so is the algorithm clear? Now this is called report noisy max, but I think it should be called report noisy argmax, because you're not revealing the optimal solution, the value or optimal objective function value, but you're only reviewing the optimal argument R star that maximizes U hat. Okay, so the premise analysis of this report noisy max is actually quite similar to what we already know from the above threshold algorithm. And to see the similarity, so let's first answer these following questions. So what is output space? Since output space is the space of all possible output R, so it outputs a particular R inside this R. And when does this algorithm output R? So then we can consider what are the random variables in this algorithm. So basically these random variables are what we call this nu, and nu R is a Laplace noise that got added to every is added to u of x of R. Yeah, for every R you're adding an independent Laplace noise. And when does this output R? When does this algorithm output R? So this is when probability of m of x is equal to R is the same as the probability that u hat x of R is larger than u hat of x of R tilde for any R tilde that is not the same as R. Right, and what this can be rewritten is the u x of R plus this nu of R is larger than the max over all R tilde that is not equal to R. U x R tilde plus nu of R tilde. Right, so this should be familiar to you if you have seen the analysis of this sparse vector technique. So what we can do is to first condition on this nu of R. So this probability, let's first like decompose this into the law of total probability by conditioning on the probability of on this particular nu R, and this is larger than and also because if we condition on this nu R, everything else is independent. All these random variables of nu R tilde is independent, and this becomes a product of all the nu tilde being R and not like taken away from this particular R larger than u x R tilde plus new R tilde. Right? And as we've seen earlier, and what this is saying is just an integral of this new new of R product over all R tilde, and this is also an integral from -infinity to this value, from -infinity to u x r minus u x r tilde minus nu of R, and then probability of nu of R tilde. Okay, and the trick, as the same trick that we use from the above threshold analysis is to define this auxiliary variable. Let's just call it nu without subscript, and we can define this auxiliary variable to be nu R plus 2 delta, and then we can replace everything here with every nu R with nu minus 2 delta, and the product of R tilde and minus nu R minus nu minus 2 delta P of nu R. And because the global sensitivity of these two is bounded by delta, so you can replace this x by x prime, and each one of them have one half of this 2 delta. So you can rewrite this as product of R tilde, and basically everything becomes the alternative space with x replaced with x tilde. Yeah. Minus nu and yeah, and it remains to bound this by e to the power of epsilon, and this is actually coming from the Laplace noise that got added. You can replace this by just this part by just the same Laplace distribution of e of nu, and this shifting operator is made possible by the fact that Laplace noise satisfies this shifting property, and then you extract this e to the power of epsilon out, and everything else on the right hand side becomes e to the power of epsilon, and P of m of x prime is equal to R. Right, so that's how report noisy max works. So it also has the same property as above threshold, that it is completely independent to the size of the output space. And each one of them has a sensitivity of delta, and you just have to pay double in terms of the noises that you add in order to get epsilon dp. Right, so the underlying argument is the same as above threshold, and there are a few remarks that I'm gonna make. So sometimes you don't need to suffer this additional factor of 2. Sometimes you can just get away with adding Laplace noise without doubling the magnitude of the noise, and this applies generally when this utility function is in some sense monotonic. What this says is that if x is equal to x tilde union with some additional individual, yeah, if it is an add relationship, then u of then monotonicity requires that u of x for any r is larger or equal to u of x prime of R. Right, so with this monotonicity, by tweaking the arguments previously, you can show that just adding one factor of delta is enough, so you don't have to do the change of variable by shifting it by 2 delta. Like another thing is that you can add other noise other than the Laplace noise. So for instance, you can add it the one-sided exponential noise. So again, Laplace noise is a two-sided exponential noise. And you can add like one-sided exponential noise. You can also add the so-called gumbo noise, which looks like what Wikipedia says here on this figure. And the interesting observation that I'm not going to talk about is that the gumbo noise version of the report noisy max is equivalent to exponential mechanism. Right, so each one of these different noise that you add to report noisy max has a like slightly different distributions, but qualitatively they all behave like more or less the same. But the version of the report noisy max where you add the gumbo noise and the fact that it is equivalent to exponential mechanism sometimes implies a more parallelizable and therefore more efficiently implementable algorithm in practice. So this is sometimes known as a gumbo max trick from the machine learning literature. Yeah, so I'm not going to be talking about it. And we can like compare the pros and cons of the report noisy max on one intuitive example of private voting. So let's say that first consider the case when one person has only one vote. Say we're voting for Trump, Biden, and say Kanye West. And each person can vote for only one person. Therefore, like you end up getting a histogram. Right, you end up getting a histogram. So and the sensitivity, the L1 sensitivity is 1 for this output that we want to release. So comparing two ways of releasing the result, so we can either just publish the whole histogram with Laplace mechanism, which gives us like epsilon dp, and by simply post-processing this Laplace mechanism by taking the argmax and releasing only the argmax, then that gives you the standard report noisy max. And just notice that this is a counting query, therefore it's monotonic. So you don't need to double the amount of noise in Laplace mechanism. So it's intuitive. The report noisy max is a post-processing of Laplace mechanism. It satisfies the same epsilon dp guarantee. So both epsilon dp. And post-processing doesn't actually help you that much in this case. And just directly outputting the results of the Laplace mechanism is giving you more information about the voting results. On the other hand, suppose we consider another type of voting. Say you can vote for as many people as you like. So a typical example of this is, say, suppose Netflix wants to figure out what is the most popular movie, and each user of Netflix can like many movies, and then in the worst case there could exist a user who like all the movies in the entire world, and we can replace that with another user who doesn't like any movie in the world, right? So the sensitivity can be quite big. So in this case, if we just add the Laplace noise of order 1 over epsilon, and then this only satisfies the say k epsilon dp, where k is a total number of data points, a total number of likes that each individual person can add. On the other hand, this is like very weak privacy guarantee if we just post-process it by outputting only the argmax. So this is typically what we want. We just reveal that based on the noisy statistics, then the winner is this particular movie. Then the analysis of report noisy max shows that they satisfy like epsilon dp with a. And in this case, the post-processing actually helps you substantially by amplifying the privacy loss by a factor of k. Okay, so I guess I have like 15 minutes or so. So in the remainder of today's lecture, I'm going to talk about I guess at least introduce the idea of advanced composition. I'll talk about privacy loss random variables, and then try explaining the ideas of how we can make use of the privacy loss random variable to achieve a stronger composition. And the hope is that by the end of today's lecture, we will be able to apply this, like without necessarily finish proving the advanced composition. Let's try applying the theorem itself to the problem of linear query release. And so that we can hopefully get some additional mileage out of this algorithm when we relax our definition of DP into so-called approximate differential privacy, or epsilon delta DP with delta larger than 0. Okay, so like the motivation is really like how can we further improve over these results? If we are willing to say like let's not like try to get the pure differential privacy, that's hope to get more utility if we're willing to choose delta to be larger than 0. Okay, and the question is that how much improvement can we get for each one of these algorithms if we use epsilon delta DP? So again, this is the definition of epsilon delta DP. When delta is larger than 0, it says that we are effectively ignoring those events that happens with tiny probability. So they say that we don't give too much emphasis on these tails of these distributions. The main theorem for the advanced composition that we're going to be covering is the following. Suppose we have K mechanism and each one of them satisfy epsilon delta DP for any epsilon delta that are larger than 0, then the whole thing, the composition of these K mechanism, M1, M2 to Mk, satisfy epsilon tilde delta tilde differential privacy with parameters that looks like the following. So recall that in the naive composition, epsilon tilde is equal to K times epsilon, and delta tilde is equal to K times delta. So this is a simple composition. The advanced composition improves over the simple composition by reducing the scaling of K to square root of K in interesting parameter regimes. So in particular, if we want this optimal epsilon tilde to be, say, on the constant level, say O of 1, and then we can choose this individual epsilon to be something like 1 over square root of K, say 1 over 2 square root of K log 1 over delta prime, right? And also let's say that delta is equal to 0. And if we substitute this into the bound, and then what we can, like epsilon tilde, what we can get is that this numerator and denominator cancels out, and we can get this is epsilon prime. Epsilon tilde is equal to epsilon prime plus 2k epsilon prime square over 2k log 1 over delta prime square. Okay, and this is equal to epsilon prime plus epsilon prime square over log 1 over delta square. Okay, so when epsilon prime is smaller than 1, when epsilon prime is smaller than log 1 over delta, when this parameter epsilon square is smaller than square root of log 1 over delta, which is like a reasonable range for reasonably strong privacy guarantee to hold, this is smaller than 2 times epsilon prime. So what this is saying that you don't need to split the budget into even pieces, each one of only epsilon tilde over K, but instead you can split it into, say, you can into epsilon over square root of K in every iteration. So ultimately, the improvement of the advanced composition is substantial when you are composing over many rounds of data access. yeah, provided that you're okay with having like non-negative, you're okay with having strictly positive delta in this epsilon delta dp. So if we want to just apply this to the linear query release, let's try applying to each one of the three algorithms. If we are applying this to the standard Laplace mechanism for releasing queries, say each mechanism satisfy at Laplace noise of delta over delta f over epsilon, then ultimately what we'll end up getting, like doing this for k times, it'll give us giving us a epsilon total of, by advanced composition, this will be square root of k times epsilon, right? Since error is delta is proportional to delta f over epsilon, so what this tells us about the error bound is that we'll end up getting 1 over n epsilon with a square root of k log k over beta. So with probability 1 minus beta. So one of the things that as we switch to epsilon delta dp is that we're going to be reserving this delta for for the delta of epsilon delta dp, and we'll be using beta for the failure probability. And yeah, I guess there's also a square root of log 1 over delta. So that's what Laplace mechanism would have an error for. So comparing to the simple composition, and which is scales linearly in k, now it scales with the square root of k. Does this advanced composition help when we apply Laplace mechanism to release a contingency table or the histogram of this data set supported on every element of the data space? Anyone? Yeah, suppose we apply Laplace mechanism to release every coordinate of this data space X. Does it help? So recall previously we get square root of X cardinality over n epsilon log of k over delta, now beta, right? So this is the bound that we got previously. Yeah, the answer is no. It doesn't help us at all, because there's no composition involved here, and the whole thing that we release in the second type of the application of Laplace mechanism is to release the histogram. So it's just one application of Laplace mechanism rather than a composition of many. And thirdly, can we apply this to private multiplicative weights? So recall that the private multiplicative weight is a composition. It's a composition of n episodes of n rounds of, and each round consists of a composition of above threshold and a Laplace mechanism. Right, so this is a composition of a total. This is an adaptive composition of a total of 2n epsilon dp, or maybe epsilon 0 dp mechanisms. So it really does help us in getting better parameters for private multiplicative weights. So recall that from the previous lecture, epsilon 0 is chosen to be 16 log of 3k over delta over n alpha, and this n from the regret analysis we can bound n by to be this quantity. Okay, and in the previous lecture we moved on by choosing this epsilon total to be n times epsilon 0, and then we end up getting this alpha is proportional to 1/3 of n epsilon, like log x log k term, right? So that was from the previous lecture. So when we have advanced composition, like here's what we can do. So assume assume this epsilon 0 is somewhat small. It is smaller than, I guess, epsilon over square root of n log 1 over delta prime. Like, let's say, make this assumption so that the previous corollary is something that we can use. Yeah, and certainly also satisfy that. So we want to make use of this. Then epsilon total is now like equal to 2 times square root of n epsilon 0. And what does that look like when we substitute this n and epsilon 0? It gives us square root of log x cardinality over n alpha square log 3k over delta. Yeah, so yeah, it's a multiply with some universal constant. So now we get square root of this n. Now it remains to choose this alpha. So what does this imply is that alpha, we can bound the error. We can bound the error to be alpha equal to some c log 3k over delta, and this delta is actually beta over n epsilon total, right? And square root. Right. So with advanced composition, we can further improve the private multiplicative weights in answering many linear queries with error that is proportional to n to the power of -1/3 to n to the power of -1/2, which with constant, say, epsilon total matches what we expect for the statistical error to be. So it's quite nice. So now, like, before I end the lecture today, so I want to just give some intuition to help you a little bit with the homework 1 on how advanced composition works. So these are also defined in homework 1. So one way of analyzing the epsilon delta dp and come up with epsilon delta dp guarantee is to work with so-called privacy loss random variable. And this is how the privacy loss random variable is defined. It is defined to be the log odds ratio or loss probability density ratio of the output random variable that's coming from 2 neighboring data set x and x prime. And the numerator is that's coming from x, and the denominator is that's coming from x prime. Okay, and this expression is a random variable because it is induced by the distribution of the output distribution when x is analyzed by this randomized algorithm. Okay, so it's a loss odds ratio that is fixed when the output is fixed, but now the output is random. Then the privacy loss is also random. So we give it a name called privacy loss random variable. So it turns out that we can construct an epsilon delta dp algorithm by bounding, by providing a high probability tail bound of the privacy loss random variable. So this is something that you're supposed to show in homework 1. It follows more or less by the definition of epsilon delta dp. Okay, so I'll leave that to you to work on. And the interesting thing about privacy loss random variable, firstly, is that when we take the expectation of this, this is a log of p of m of x and p of m of x prime. Yeah, or let's do x prime, right? Okay, so this is a definition of the callback laplace divergence of the two distribution. Which is defined by log of p x y over p x prime y. And secondly, like when we compose this privacy laws random variables over multiple rounds of data access, let's say that you have randomized algorithm M1, M2, all the way to MK. And the composition of this is simply to take the union of all their outputs. Then for now, let's consider these randomized algorithms are specified ahead of time and they are fixed. Then the privacy loss random variable of the composition of them all is log of p m1 x of y1 p m1 of x prime of y1 multiply with m2 x of y2 to mk of x yk m2 of x prime y2 mk of x yk. Why is that? And this is because of the independence of the independence of y1 and y2 to yk. Right, suppose this mi is chosen adaptively. Yeah, but by the way, this is nice because it becomes a summation of the privacy loss random variable of the individual. This becomes there's a summation of these, and let's say that mi is chosen adaptively as a function of y1 to yi minus 1. Then what happens is that the composition also factorizes, but now the factorizes will have this conditioning with a law of total probability. So instead of factorizing this into the product marginals, now it factorizes into m2 of x y2, and given m1 of x is equal to y1, and all the way to p of m k of x of yk given y1 to yk minus 1 are all set in stone, right? So this similarly factorizes into a product of privacy loss random variables. Each depends on the output of the previous round of the computation, right? So the idea of advanced compositions is to work with this summation and of the sum of random variables that's either independent. So in this case, it's independent, and in this case, it is you can be manipulated into a martingale, and then like do a concentration. So the idea is really that sometimes the privacy loss random variables are positive, other times it's negative. When we sum over a bunch of them that are independent, they will cancel out with each other. So we can hopefully at the end of the day get a tighter bond, tighter high probability bond of its tail after composition. Yeah, so I'll leave the formalization of this argument to the next lecture. So I'll stop here. I'll see you guys on Wednesday.